It's science time with Wobbies.
Hello, it's Fano. So today we're looking at this base and acids reactions worksheet. What you needed to do was balance the symbol equations and also balance the word equations. A very common question that I got from students was, how do I know what it's going to turn into? How do I know what the reactants were? And it does involve a little bit of problem solving, but there are some basic rules that we can follow first. So if we look over to this slide, you might have seen this in a different form somewhere else. We have got neutralization reactions of acids. If you have an acid and a metal oxide, you get salt and water. Acid and metal hydroxide, you get salt and water. You also get salt and water, but one that makes something a little bit different, a little bit spicy, a little bit, me, is acids and metal carbonates. That gives you salt, water, and carbon dioxide. Now, key to this is knowing kind of what these things are. So if we think of an acid, its key chemical property is that it donates hydrogens, donates H pluses. Sometimes we'll call that a proton. Okay. A metal oxide is an ionic compound, and actually all of these are ionic compounds. So that's something to keep in mind for later. Okay, so our metal oxides, we'll just use our friend magnesium. So magnesium and oxygen, that's it. That's a metal oxide. It's a metal ion and an oxide ion. So remembering that Mg2 plus is the ionic form of magnesium, and the ionic form of oxygen is O2 minus. So what they've done is they've swapped 2 electrons to get their full outer shell, forming an ionic compound. Now, if we have what's a metal hydroxide, this involves the hydroxide ion. So again, using magnesium, it's going to make friends with the OH minus ion, which is a polyatomic ion. And because it has, we'll get rid of that charge, that's not meant to be there, but because it does have that minus charge, we're going to need 2 hydroxide ions, because the 2 OH minus means that it will marry up nicely with the 2 positives from the magnesium. And last but not least, our metal carbonate. I'm not sure if you remember, but our carbonate anion looks like this. So this is a carbonate, and that is going to go through and, well, we've been using magnesium, so magnesium carbonate, right? So you can see now, looking at this, that metal oxides and metal hydroxides, there is no way that they can form carbon dioxide because they don't have carbon in them. Anything that has a CO3, you should think to yourself, okay, when this mixes with acid, it's going to form bubbles, it's going to form carbon dioxide gas. But it's still going to form a salt and a water. So we've gone over a few words. We've gone over anions, negative ions, cations, positive ions. We've talked about ionic compounds, which are neutral compounds where atoms have swapped electrons to form ions, forming a neutral compound. Neutral as in they don't have charge. They might not necessarily be pH neutral, but that's something we can get into later. And the one thing that I haven't gone over is alkali. An alkali is a soluble base. Now the next section that will help you with this, and this is something that thankfully it gets shown to you in the exam, is this table of ions. Now, with ions and with our table of ions, we're going to be shown the symbols, but we will not be told the names. You need to use your memory and a little bit of practice to be able to figure out what these ions are. Now I'm going to go through these and write down the names so that we have a point of reference for while we're doing the worksheet. definitely pay attention to this, because to increase your memory and your recall, it's really good to not only hear the words, but see the words. And that is, the purpose of doing this video. So for our names of our cations, we have got NH4+. Okay, this is the ammonium ion. Ammonium. Okay, then we have our sodium ion. So these are all +1 cations because the table is organized a little bit like the periodic table. It's organized by what type of ion they form, except it also includes polyatomic ions, which is why we've got ammonium. Now, this is our sodium ion. K is for potassium, so that's the potassium ion. Ag. Now, this one you can remember by this really great joke. What did gold say to silver? Ag. Not a great joke, not my best joke, but it's a joke, so it helps you remember. So silver is the one that has G in it, gold is the one that has U in it, because that makes perfect sense. And then last but not least, in our plus ions, we have got hydrogen ion, which is sometimes called a proton. Now, if we go into our +2 ions, so these, even though you can't see the list, maybe have your worksheet open while you're having a look at this video. Definitely worth doing. So the first one that's up there is Ca2+, and that is the calcium ion. Then we have our buddy Mg2+, who we've talked about already in this video, which is the magnesium ion, We have got the copper 2+ ion, and like I said, that's copper, Cu2+, copper ion. Then we have Pb, 2+, Pb, think plumbers, think lead pipes. That is our lead ion. Then we have Fe2+. Fe2+ is the iron 2 ion, and the reason why I've got those Roman numerals in there is because iron can form different types of ions. This is because it's in the transition metal section of the periodic table. Thankfully, this is the only one that you have to worry about for level 1, but as you sort of go through chemistry and also biology, you learn about these different types of ions that metals can form. So moving on, we've got Ba2+. What do you do with dead bodies? You bury them. So that's your barium ion, and I've sort of run out of space, so we'll go back up the top. We have got Zn2+. And this is your zinc ion. Alright. So now our last group of ions is the 3+ ions. Well, our last group of cations are the 3+ ions, and we only have 2. So we have Al3+. This is aluminum or aluminium, depending on where you're from. Aluminium ion. And then we have the Fe3+ ion. And so this is the different type of ion that I was telling you about. So this is the iron NO3 ion. So it's quite cool that these Roman numerals actually tell us what charge ion we're dealing with, and that can be very useful when it comes to figuring out symbol equations from names. So keep that in mind. Okay, so now we're looking at our names of anions. So anions, onions, they make you cry. That's negative. So we're looking at our names of anions, and we're going to start with our negative. So one negative. Anions, onions, they make you cry. That is the best way that I have come up with remembering them. And, you know, cations, because cats are positive. It's also a good one. So anyway, we're going to start off with a polyatomic ion. This is hydroxide. Hydro as in hydrogen. Oxide as in oxygen. Chemists are lazy. We don't want to say the hydrogen-oxygen ion. That's way too many words, too many letters, too many, you know, just too much. So we smush it together, we make it the hydroxide ion. And we're talking with anions, so there's going to be a lot of ides at the end of words. And this is quite useful in names because it does let you know, just by looking at the name of a compound, you know, A, that it's an ionic compound, and you know which one is the negative ion and which one's the positive ion. So like sodium chloride, sodium and chloride, it's not sodium chlorine. If it was sodium chlorine, we'd be dealing with the atoms, but because it's chloride, we know that it's an ionic compound, that it consists of sodium and chloride. And speaking of chloride, here is our Cl minus. So this is spelled this way, chloride. Chloride ion. And then we have NO3 minus, another polyatomic ion where chemists have decided to smush the words together. So we've got nitrogen and 3 oxygens, and following that not quite perfect chemist logic, this is the nitrate ion. Okay? So you might hear about nitrates being added to fertilizers. This is what they're adding. 1 nitrogen, 3 oxygens. Now we have one that sometimes gets called bicarbonate, sometimes gets called hydrogen carbonate, but we're going to go for hydrogen carbonate because that is the more accurate term, I feel, the more modern term. So this is the hydrogen carbonate ion. And our last one is the fluoride ion. So fluoride is what's in toothpaste. And it's, instead of being like the atom fluorine, it's following the same rules as chlorides and oxides. We are adding "-ide" to the end. And that is all of our negative, so our 1 negative ions. Now, if we go to 2 minus, we only have 4 that we need to know. One very common one is our oxide ion. That is followed by our sulfide ion. Sulfide, you might find in some places that sulfide or sulfates or whatever start with a PH. Thankfully, they decided fairly recently that we're just going to use an F for everything. It makes more sense. It makes spelling a lot easier, which is good, especially if you're like me and always used to get them confused. Now, our third 2 minus ion that we need to know is carbonate. So you see that carbonate is CO3 2 minus, and then if we remember about hydrogen carbonate, it was HCO3 1 minus. The reason why there's a difference in charge is because we've actually added a positive charge, just one, to the hydrogen carbonate. So hydrogen carbonate is a carbonate ion with a hydrogen ion, H+. So it's brought our charge down to -1. So I'll just write that down. That is a carbonate ion. And our last one, another classic example of chemists smushing words together, sulfate ion. Sulfate because there are 4 oxygens in this polyatomic ion and 1 sulfur. Okay, so now that we know the names of our ions, this sort of gives us a way for us to start puzzling out what could be formed from these reactions. Now, if I slide on over to the worksheet, for our first one, zinc hydrogen carbonate and sulfuric acid goes through zinc sulfate and water and carbon dioxide. So we'll start off with zinc hydrogen carbonate. So this has got a Zn2 plus and 2 hydrogen carbonate ions. Okay. So if we look at this, we can see that the zinc has a 2 plus charge, the hydrogen carbonate has a -1 charge, so that is why there's that little 2 down the bottom. Now, if we move on to sulfuric acid, you will see SO4. Thinking about our ions, I'm going to change color. So SO4 is SO4 2 minus. We can see that there's 2 H's there, and that's because we need the 2 positive charges to balance out that 2 minus charge. Okay? Hopefully you're following along. If not, just keep buckled up. Now this is the bit where you need to do a little bit of puzzling, a little bit of problem solving, and also keep in mind carbonates form carbon dioxide. Okay? That is key. That is crucial. So if we look, we have got a zinc. That is our 2 plus. In our reactants, so we've got a positive charge in one of our reactants. This is going to react. When we react, we form new molecules, so new bonds are being formed. The zinc isn't going to, it's not a reaction if the zinc is just bonding back to the hydrogen carbonate. So what's going to happen instead is the zinc is going to bond to the sulfate. So Zn2 plus SO4 2 minus gives you zinc sulfate. This is an ionic compound. This is a salt. Okay, we know that hydrogen carbonates plus acids give you a salt. They give you water and they give you carbon dioxide. Now we can check that this equation is balanced by counting the amount of atoms on each side. So on the product side, we have got 4 plus 2, because 2 times 1 is 2. 4 plus 2 plus 4. So 4 plus 2 plus 4. We've got 10 oxygens. Okay? Now on this side, we have got 6 oxygens here, and we've got 4 oxygens here. 4 plus 6 is 10. So those are balanced. If we count our hydrogens, we have got 1 times 2, because the brackets indicate and the little subscript 2 indicates that there are 2 HCO3 minuses. So we've got 2 hydrogens plus 2 hydrogens, that's 4. 2 times 2 is also 4, so that's balanced. Okay? We have got 1 sulfate ion on each side and 1 zinc on each side. We also have 2 carbons on each side, because again, CC, okay? It is balanced. Now let's move on to our next equation. This is aluminum oxide plus hydrochloric acid. Okay, we have got a metal oxide. There is no carbon involved, therefore we're not going to get any carbon dioxide forming, but we still will get a salt which I'm just going to write up there, and water. But the question is, what salt will we get? And to do that, I'm going to break up my reactants into their ions, and I'm also going to, I might as well write out the symbol equation for that side while I'm doing it. So we have got Al, because that's aluminum, that is 3+, and O2 minus, plus hydrochloric acid, which is H+, plus Cl minus. Now, the first step in balancing equations, symbol equations, is you need to make sure that you're dealing with neutral compounds unless it's indicated that you're dealing with ions, which at this stage we're not. So there is a really easy method called the swap and drop method when you have ions that have two different charges. So what you do is you will get Al2 plus O3. So what I've done is I've taken the charges, so the charge of O2 minus, I've given that to the subscript, so that's the whole drop. We've dropped it down to aluminum, so it's Al2 and 3 oxygens. Now, if you were to look at that in the way that I did previously, it would be Al3 plus, Al3 plus, O2 minus, O2 minus, O2 minus. That is a total charge of 6 minus. Then on the positive side, we have a total charge of 6 plus. So that means in our metal oxide, for every 2 aluminum ions, we're going to have 3 oxide ions. Okay. Hydrochloric acid is already balanced because it is H plus, what's 1 to 1? So it's Al2 O3 plus HCl goes through to something. So we've got water that takes care of our H2O. We just write that in, H2O. But we've got, think again, what is happening with our positive and negative ions from the reactants? They're going to be being rearranged in a different sort of bonding formation. The only thing that they can form is cation plus anion, positive plus negative. So we are going to get aluminum chloride. Now you'll be thinking to yourself, how do I know how many aluminums to have and how many chlorides to have? Well, we need to think about it in that same way. If we have Al3 plus, we need to add enough negative charges to cancel out, to balance out that 3 plus. So we need to add in 3 negatives. So we're going to add a little subscript under the Cl of 3. All right. So now we have got 2 hydrogens on one side, 1 hydrogen on the other side, 1 oxygen on one side, 3 oxygens on the other side, 2 aluminums on one side, and 1 aluminum on the other side. The first thing I'm actually going to do is balance out my chlorides. So to do that, I'm going to add a nice 3 in front of my HCl. So now I have 3 hydrogens on one side and 2 hydrogens on the other. That doesn't really make sense, but we'll leave it there for now. Now, because you want to balance your cations and anions first and then go into your hydrogens and oxygens. So let's see what happens if we put a 2 in front of the Al, the aluminum chloride. So that's going to give us 6 chlorides to deal with. So instead of the 3, I'm going to have 6, okay? So 6 HCl. So we've got 6 chlorides because 2 times 3 is 6. And we've got 2 aluminums, and we just need to sort out our oxygens. So we've got 3 oxygens on one side, and we have got 1 on the other side. We have got 6 hydrogens on one side and 2 on one side, and the easiest way to fix that is to add a 3. So 3 times 2 is 6, so now we've got 6 hydrogens on each side, and we've got 3 oxygens, which matches perfectly with our aluminum oxide, which has 3 oxygens. Okay, so these things they do require problem solving. They do require a lot of thinking, and if you do struggle with these questions, there is no reason that while you're doing the exam, you can answer everything you know that comes easily and leave these ones till the end where you have a little bit more time to problem solve. Moving on to question number 3. We've got lead hydroxide and nitric acid. Nitric is not something that we had in our ions chart, but we know that acids must contain a hydrogen because they're hydrogen donors. So there's an H there. And nitric, there must be a nitrogen in there. We are going to use our nitrate ion. So we've got H plus and H3O minus. And lead hydroxide, we've got Pb2 plus and a hydroxide ion, but because hydroxide has a charge of 1 minus and lead has a charge of 2 plus, we know that we're going to need an extra hydroxide to get a balanced compound. So this is a metal hydroxide like we were talking about earlier. So overall we would have Pb open bracket because it's a polyatomic ion, close bracket, and just like in maths, if something's in brackets, that's what gets multiplied by the 2. Because if we didn't have the brackets there, it would look like one lead, 1 oxygen, and 2 hydrogens. And again, our acid is nicely balanced already. Now this is going to form a salt, which is a cation and an anion, and water. Now it's important when you're doing word equations to write water as water, and when you're doing symbol equations to write water as H2O. Obviously, we're all fairly aware that water is water and H2O is the same thing, right? But if we're talking about word equations, we need to use the words, not the symbols, and H2O is a symbol. Now, our ions that we have left to play with is we have the nitrate ion. So it's going to be something nitrate. Because our products are the reactants and where they've broken apart and then they've joined back together in a different way, that means that we must have lead nitrate. Because if we were to have hydrogen nitrate, that's just nitric acid, and that means there wouldn't have been a reaction forming. So lead nitrate, you'll notice that OH minus and NO3 minus have the same charge. That means it's going to have the same sort of formula when it comes to forming the ionic compound with lead. So that means you're going to get 1 lead for every 2 nitrate ions. Okay? Now, all that's left is the balancing. So I'm going to change pen color. So on this side, we've got 1 lead, 1 lead. Awesome. On this side, however, we've got 2 nitrates, and we want to balance it out. We have got 2 nitrates on one side, 1 nitrate on the other side. So that's the first thing that we're going to change. We're going to make it so that there's 2 nitrates on each side by adding a big 2 in front of the nitric acid, HNO3. Now we've got PbOH2. So we've got 1 lead on each side. Beautiful. Now we've got 2 nitrates on each side. Let's count up our hydrogens. So we have got 2 on this side. However, on this side, we have got hydrogen times 2, which is 2. And we've also got 4 hydrogens altogether. So that means we're going to add a 2 in front of our water. So now we've got 2 waters. Now that means we have got 4 hydrogens here, 4 hydrogens on the other side. Now let's just double check our oxygens. So on the reactant side, we've got 2 oxygens plus 6, so 2 plus 6 is 8. So we'll just write that down so we don't forget. And then we have got 3 times 2, which is 6, plus 2, which is 8. So that means our equation is balanced. Now, that is our metal oxides. That is our metal hydroxides. And now I'm going to do an example of the carbonates. Carbonates can be a little bit trickier to balance because you're dealing with an extra product, but the first one was done for us, and that is basically the same sort of formula that we're going to do, same sort of method, I should say. So let's just get rid of all this and do our next question. Go away. Okay, so I like to break these up into our ions. So we have got sodium. This time I'm going to do the unbalanced symbol equation up the top just so it's a little bit less messy. So we've got sodium, we've got a carbonate. So this is 2 minus, so we're going to add in an extra sodium. Plus, so this is the stuff that you would write in pencil or you'd just cross out and not leave in your final answer, just to clarify. Plus hydrochloric acid. This is our HCl. And again, it's a 1-to-1. Goes forth, and it is a carbonate. So I'm going to write the carbon dioxide first so I don't forget. Plus water, plus our mystery salt. So we've got a sodium and a carbonate. We also have a chloride to play with. So we're actually going to form sodium chloride. Okay? And so that means we have got CO2 plus H2O plus NaCl. We have got 2 sodiums on this side, 1 carbonate plus HCl going through to CO2, because the dioxide means CO2, means O2, sorry, plus water plus NaCl. And forgive me that it's getting a little bit messy. That's just how I like to live my life. Alright, so one thing that you'll notice is that your carbonate actually splits into the carbon dioxide and it lends one of its oxygens to the water. So if you have one carbon dioxide and 1 water, it's going to be balanced. But where it gets tricky is we have got 2 sodiums. So we're going to add change color, it'll be yellow this time. Added 2 here, 2 in front of my NaCl. So that gives me 2 on each side. But now I've got 2 chlorides on one side and 1 chloride on the other. So we added 2 in front of the HCl. That gives us 2 HCl, which means we now have 2 chlorides on each side. And it also means we have 2 hydrogens on each side, because big 2 means there's 2 HCl's present. So if we were to write all of our things out in ions, it would look like this. And we would also have an extra Na plus, just add the arrow in, and an extra Cl minus on the other side of our equation. So you can see that there's 2 chlorines, 2 chlorines, 2 sodiums, 2 sodiums, 1 carbon, 1 carbon, 3 oxygens, 3 oxygens, 2 hydrogens, 2 hydrogens. It is perfectly balanced. Now I'm going to go on to my last example that I want to help you with. Sulfuric acid plus barium hydrogen carbonate. So I'm going to change to my blue pen again. Sulfuric acid, it is H plus and SO4 2 minus. Because remember, acids are hydrogen donors, so we need to have a hydrogen in there. And I know that there's 2 hydrogens because my sulfate ion from the sulfuric part has a 2 minus charge. Plus barium, which is Ba2 plus, hydrogen carbonate. Hydrogen carbonate is our HCO3 minus. We're going to need 2 of those in order to make sure that the barium 2 plus is balanced with the 2 negative charges. 2 plus, 2 minus, samesies. And so this is going to give us Ba and then open bracket HCO3 because we're multiplying the amount of hydrogen carbonate ions by 2. Then we draw our arrow in both, symbol and word. Now we've got a carbonate. Even though it's hydrogen carbonate, it is still going to form CO2 because it's, in terms of like chemically easy things to do, it's really easy for carbonates to split into carbon dioxide. This is why we add baking soda, bicarbonate of sodium bicarbonate to our baking, because it reacts in our mixture and it forms bubbles, and that gives us, like, if you're making scones, you want to add baking soda or else you will be eating rocks, okay? Now we've got carbon dioxide. We know we're going to form water. Oh, I've been doing this back to front. Again, important to remember things. So we're just quickly going to fix that up. So it's going to say carbon dioxide plus water, which translates into symbol language as H2O, plus a salt. We have got 2 perfectly sort of equal and opposite anions and cations. We have our sulfate ion and we have our barium ion. So this is going to be barium sulfate. Which goes through to BaSO4. And remember, we don't include charges in our neutral compounds. So now we just need to double check that we've got enough of everything. And I can already tell that there isn't enough carbons because of that little subscript there. So we're going to have 2 carbon dioxides. If we have 2 carbon dioxides, I'm going to write them in just to help visualize. We've got 2 carbon dioxides. That means we have a total of 4 oxygens plus 1, which is 5, plus 4, which is 9. Now if we add 3 times 2, that's 6, plus 4, that's 10. So we're not quite right here. Now if we have a look at our hydrogens as well, we've got 2 hydrogens plus 2, so in total we've got 4, but we only have 2 hydrogens on this side. So we're going to have to add a 2 in front of our water. So now we've got 2 times 2 is 4. We've got 4 on each side now. So I'll draw those in. That means we have 2 times 2 oxygens, which is 4, plus 2. So 4 plus 2 is 6, plus 4, which is 10. And so that is our balanced symbol equation, and I'm going to write that out nicely. So the full balanced equation for this one is 2 CO2, 2 H2O, and 1 barium sulfate. So you don't actually change anything on the reactant side, it's just what's on the product side. So I hope that was really useful. Now that you've seen examples of how to do the different equations, or the different types of equations, have a go at finishing the worksheet yourself, then take a look at the answers that I'll be posting as well. Now, I hope you have a beautiful day, beautiful afternoon, stay safe, be kind, ka kite ano.